So Unit 10 or Chapter 10 is the second half of our chemical bonding. We're going to discuss molecular geometry and the hybridization of the atomic orbitals. So exactly how are our atoms bonding and sharing those electrons? The Lewis diagram often makes molecules look flat, two-dimensional, but really they're three-dimensional and fill up the space of the X, Y, and Z axis with electrons either in a bond or in lone pairs on the atom. Since electrons repel each other, they often spread out to minimize this repulsion. So the shapes can be predicted using the valence shell electron-pair repulsion, or VSEPR. Knowing the shape of the molecule can lead to explaining and predicting the chemical and physical properties of that molecule. So the molecular geometry is the molecule's geometry affects the properties such as melting point, boiling point, density, and the types of reactions it undergoes. Bond angles and lengths must be determined experimentally. We can predict these with the geometry of the molecule. Based on electron pairs in the valence shell, based on the fact that electron pairs in the valence shell repel each other. The valence shell is the outermost electron-occupied shell of an atom and holds the electrons that are usually involved in the bonding. Valence shell electron-pair repulsion, or the VSEPR model, accounts for the geometric arrangements of electron pairs around the center atom, or the central atom, in terms of the electrostatic repulsion between the electron pairs. So there's two general rules. Number one, as far as the electron pair repulsion is concerned, multiple bonds are treated as a single bond. It's good for qualitative purposes. In reality, though, multiple bonds are larger than single bonds. The electron density occupies more space. The second general rule is that if a molecule has two or more resonance structures, we can apply the VSEPR model to any one of them, and formal charges aren't usually shown. So it's a good first step to categorize the molecules based on having lone pairs on the center atom or not having lone pairs. If there's no lone pairs on the center atom, then we have 5 different geometries to choose from. Linear, where you have one atom attached or 2 atoms attached with no lone pair on the center. Trigonal planar, you have 3 atoms attached, no lone pairs. Tetrahedral, you have 4 atoms attached, no lone pairs. And then 4 and 5 is when we start breaking the octet rule, or having an expanded octet. You have trigonal bipyramidal, 5 atoms attached, and octahedral, 6 atoms attached. If there are lone pairs on the center atom, then we have many more types of geometries possible. The electrons in the bonds are held by the attractive forces exerted by the nuclei of the 2 bonded atoms. They then have less spatial distribution than the lone pairs. So they take up less space than the lone pairs. The lone pairs occupy the most amount of space, and they experience the greatest repulsion from the neighboring lone pairs and bonding pairs. If there's more than one central atom, like in many organic substances, the shape around each of the central atoms is described. So for example, here we have CH₂OH. So if we look at the carbon atom, carbon has 1, 2, 3, 4 atoms coming off of it with no lone pairs. So the carbon atom would be tetrahedral in shape. The oxygen has 1, 2 atoms coming off of it. It would also have 2 lone pairs. So the oxygen atom has a bent geometry. There are 4 different guidelines for applying the VSEPR model. First, you want to draw the Lewis structure. Then you want to count the electron pairs around the center atom, bonding and lone pair, and treat multiple bonds as though they were single. And then you're going to predict the geometry. A lot of times you might see things like A for the center atom, X for the number of atoms attached, and then E for the number of lone pairs on the center atom. That's called the classification, and then using the classification we can match it to one of our geometries. In predicting bond angles, lone pairs repel each other more, or lone pairs repel other lone pairs or bonding pairs more strongly than bonding repels other bonding. So the lone pairs are going to change the geometry of the non-lone paired molecules. So you do need to know your bond angles along with the geometry. None of that's given to you on the test, so you're going to have to remember it. So for example, we have SiBr4. So if we draw the Lewis structure, silicon would go in the middle, and then we would have 4 bromines coming off. And the bromines would have satisfied octets. My silicon has also got 8 electrons being shared. It could break the octet rule, but it doesn't need to. So in this case, I have a center atom, and then I have 4 atoms attached to it. So it's tetrahedral in shape. And tetrahedral atoms have a bond angle of 109.5. Now CS2, carbon would be in the middle. I would have 2 sulfurs coming off of the carbon. I would satisfy the sulfurs, and then carbon would not be satisfied. So I do actually have to have 2 double bonds. So I would have AX2 as my class, which means I am linear in shape. So my bond angle is 180. Now NO3, if I was to draw the Lewis diagram, I would have nitrogen with 3 oxygens being bonded. I would satisfy my oxygens, but then my nitrogen's not satisfied. So one of my oxygens is double bonded. Even though we have resonance, it doesn't matter which oxygen we bond. The geometry would still be the same. So I can just look at this one resonance structure. So my geometry would be AX3. So this would be trigonal, pyramidal. Not pyramidal, planar. So the bond angle would be 120 degrees